Drive and discuss the moment generating function technique. Solution: let phi x1, x2, xn be the joint probability density function of a n random variable x1, x2, xn. These n random variables may or may not be observations of the random sample from some distribution that has given probability density function f of x. Let y1 is equal to u1, x1, x2, xn. We are to find gy1, the probability density function of the random variable y1. For this, let us consider the moment generating function y1. If it exists, it is given by mt is equal to e bracket starts e raised to power t y1 bracket close is equal to integral minus infinity to infinity e raised to power t y1 g y1 dy. For the continuous case, first we get the value of gy1, then putting the value of gy1 in 1, we get the value of mt. For this, let us consider integral minus infinity to infinity so on integral minus infinity to infinity exponential of t u1 bracket starts x1 x2 so on xn bracket close square bracket close phi bracket starts x1 x2 so on xn bracket close d of x1 d so on dxn, which is assumed to exist for minus h is less than t is less than h. Let us introduce a new variable of the integration. y1 is equal to u1 x1 x2 xn so on xn. y2 is equal to u2 x1 x2 so on xn so on yn un x1 x2 so on xn. Let us assume that these functions define a one-to-one transformation. Let xi and wi y1 y2 so on y1 I is equal to 1 to n. Equation 3 denote the inverse functions. Also let denote the Jacobians of the transformation using the transformations 2 becomes integral minus infinity to infinity integral minus so on integral minus infinity to infinity e raised to power t y1 modulus of j phi w1 w2 so on wn dy2 so on dyn dy1 so on. This is equation 4. Since we know that modulus of j phi square bracket starts w1 bracket starts h1 h2 so on hn bracket close so on wn bracket starts y1 y2 so on yn bracket close square bracket close is the joint probability density function of y1 y2 and yn. The marginal probability density function of gy1 of y1 is obtained by integrating this joint probability density function on y2 y3 so on yn. Since the factor e raised to power t y1 does not involve the variable y2 y3 and so on yn, therefore 4 may be written as integral minus infinity to infinity t y1 g y1 dy y1, but this is by the definition of moment generating function mt of the distribution y1. That is we can compute e is equal to square bracket exponential of bracket starts tu1 bracket starts x1 comma so on xn bracket close, square bracket close, we have the value of e, bracket starts small e raised to power t y1 bracket close, where y1 is equal to u1 bracket starts x1 x2 so on xn square bracket close. This fact provides the another technique to find the probability density function of a function of several random variable. If the moment generating function of y1 is that certain kind of the distribution, then the technique uniqueness of the problem y1 has that kind of distribution. When the probability density function of y1 is obtained in this way, say that the moment generating function of a technique is used.